Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis, and we're in Chapter 7, part of this playlist that I'm generically calling Classification Analysis. And let's jump to today's topic, which is linear classification into several groups. So the setting is we have K groups, and we're in a multivariate setting, so each observation is a vector of length p with p variables. We have to assume that the covariance structure is the same or equal for the K groups. We generically call it sigma. And we estimate sigma with our pooled sample covariance matrix. So it's a linear combination of the sample covariance matrix divided by its degrees of freedom associated with it, which is capital N minus K. Now E is the error matrix, and I'm going to point you back to one-way MANOVA for more detail on that. Capital N is the sum of all the sample sizes in each group. K, of course, is the number of groups. Now the setting is we have data, and the data consists of vectors. We have in vectors, and then associated with each of those vectors is a group. So it's a known group and a known vector. And from that, we want to classify the next observation. We don't know its group, but we know the p variables associated with that observation vector. And what group do we assign it to? So the strategy is we look at the Mahalanobis distance, or the statistical distance from that new y vector to each of the group mean vectors. And whichever has the smallest statistical distance, we assign that new observation to that group. And so how to do this, we calculate a DI squared, which is Mahalanobis distance, or a statistical distance from the new observations to each of the mean vectors for each groups. But we generically let it be I, and then of course then we have to do it for group 1, 2, 3, the ith, the kth. So we get K statistical distances, and the one that's smallest, that's where the new observation goes. Now, to me, this is quadratic, but I introduced this as a linear classification rule. And so to show that it is linear, what we do is we change this a little bit. So what we do, so here it is in this line, we multiply it out. So it ends up being this line here. Now, since they're all numbers, we can take the transpose and it doesn't change it. So this number in the middle ends up, we can transpose it, and then we get two of them. So, but when you're calculating distance between the new observation and each mean vector, this first term adds nothing to the distance. It's always the same for every group mean vector. So we can almost we can get rid of it, and the rule still applies. And then if we take it times a minus 1/2, we get this linear classification function right here. And it's linear in the y's because it's a linear combination of the y vector right here. This is a constant in terms of y. This is a linear combination. So it is, in fact, a linear classification function. And so, but this one is, since we took it times a minus 1/2, we want the largest linear classification function, and then that's what we assign the new observation vector to. Okay, so really both are 100% equivalent, di squared and li of y. They're 100% the same. Di, you look for the smallest statistical distance. Li, you look for the maximum value, and they're equivalent. And I like di squared because it's a statistical distance, and in R, there's a Mahalanobis function that makes it very easy. Now here's a subtlety that I think can be confusing to some, that the linear classification functions are different from the linear discriminant functions, whose coefficient are the eigenvalues of this matrix product, inverse of VH. I'm a point, yeah. But so note, in many cases, we don't need all the discriminant functions to effectively describe the group differences. But when you're classifying a new observation into one of the K groups, we have to have all K classification functions to assign that new observation. And the example we do will help highlight that. And we're going to look at an example from an FTP site given by this. And we're going to look at the data T617 fish dat. And it's Bait and Tack and Bader in 1958 compared judges' scores on fish prepared by 3 different methods. 12 fish were cooked by each method, and several judges tasted fish samples and rated each on 4 variables. Now, each entry is an average of the score for the judges on that fish. The 4 variables were aroma, flavor, texture, and moisture. So we fire up R here. We load the library mass because that's where our linear discriminant function is. We read in the data. There's no headers, so we have to assign it names. And then let's print the first 6 observations, which is called the head. Now, method, of course, is the fish, and these values take on 1 to 3. Let's calculate the sample sizes for each group, which is 12 for each method of cooking. We calculate the mean vector by group using this function here. And this is it. There's 3 groups, and this is the mean vector. So this, in our new observation, will be compared against each of these mean vectors. We have to calculate the pooled estimate of the covariance matrix, so SP, and there is the function. As always, I will list this in the comments so you can copy and paste it into your code, and that's it. So now we fit a linear discriminant analysis, the LDA function, to our data. So method is modeled as aroma, flavor, texture, and moisture. And then when we look at fit, it produces what's called prior probabilities, which we're not going to really cover. And here are the group means, the same group means that we just printed out above. And these are the 2 linear discriminant functions. Now, LD1, it maximizes the statistical distance between all of these group means, right? That's what it's for. And LD2, also, it helps. It's the next maximum way to differentiate the means. It's actually orthogonal to LD1. But if you look at the proportion of the trace or the eigenvalues, this first linear discriminant function is 96% of the total. So we don't really even need the LD2 when we're discriminating between the group means. Now, that's not part of this video, but I wanted to highlight that. So we're only going to use one discriminant function. Now let's predict so let's use this model and then put our data back through it to see how well it predicts. And so we predicted LDH, and I need to make this smaller. So this is the predicted groups. So this is group 1, group 2, group 3. Right? You can see that they are a little bit different. Now, this is just made up example. So if we have a new observation 5, 4, 6, 5, where will we classify it? So you use Mahalanobis distance, and this is the mean vectors by group. This is the pool. SP is the pooled covariance matrix, and it calculates the Mahalanobis distance against each of those mean vectors, and that's 42, 29, and 12. So 12 is clearly the smallest, so we would classify this observation into group 3. Now you might wonder, it's like, why would we classify somebody in, for a method of fish? I don't know. It's just a made up, example. So, maybe some judge taste tested a fish, but forgot which method they used. So they need to go back and try to guess what method of fish that they used to cook it. So if the next vector 5665, if we were to look at the Mahalanov's distance against each of the mean vectors, then we would classify it into group 1 because it has the smallest distance. Now let's do this for every observation. Let's see if our method would actually classify the data, that we know the correct method of cooking, if it would classify them right. And so this is these next two steps are the way we do it. So each observation, so each, the first observation, our sample, we compare it against the mean vectors for each group, and this is it. So we would classify the first observation into group 1. We'd classify the second group into group 1. The third observation we classified into 4. So we're just seeing how well our rule is going to be applied. So normally I wouldn't print this, but I kind of want to show you. So really somehow we need to pick off which group is smallest. And that's what this next function does. The which dot mean, so it goes in and finds which component is smallest, and it puts that number. And so I call predict fish. And now let's use the predict method that we got from the LDA function. So if we predict using our fit, which is the model that we fit with, and we want class, and we just table or compare each of these with the table, notice that they're 100% in agreement, as they should be, right? And so to use the built-in function, so much easier. Now let's look at the actual values in our data against the predicted values, and notice that we misclassified 9 observations. So the actual fish cooking method was 1, and we predicted 9, but we predicted 3 of them were method 2 when it should have been 1. And so you can see that there's 6, 7, 8, 9 observations misclassified. Anyway, so we're about 12 minutes. I'm going to call this video finished. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.